Example 8. Everybody got notes? Okay. A 3,000 Newton car. Oh, I gave you mg. Let's make a little note that 3,000, because it's newtons, I gave you the weight, not the mass. At rest, I should probably underline mentally or actually the phrase at rest. At the top of an incline, 3 meters high and 30 meters long is released and rolls down the hill. What's its speed at the bottom of the incline if the average friction force is 200 newtons? I like this question. What's this question asking me to find, Alec, now that you're done yawning? Speed or velocity? I picked, okay, which suggests use a scalar approach. Is there a change in height?
Yes.
Is there a change in speed? Is there a yucky, curvy path? No, but the fact that they said speed, and I also see them talking about friction force, I'm going to try doing this with energy. I might be able to do this with kinematics. In fact, I could if they had given me a way to calculate friction. Do you see a mu anywhere? Okay. How am I going to start this? What am I going to do first? I've taught you. I've given you some tools. What would you do if you're trying to solve this? Hopefully there's something you'd think of doing right away. Even before that. I'm an adult. Absolutely. I have no idea what's going on here. So it looks like there's an incline. Yeah. We have a little car at rest up there. And it looks like the height of the hill is 3 meters high. Excuse me. And the distance of the hill is 30 meters. Okay. I'm going to try solving this using conservation of energy. So I'm going to start out writing KE initial plus PE initial equals KE final plus PE final plus heat. Wait a minute, Mr. Dewick. They didn't talk about heat. Or did they? What have they said? There's a friction force. We are losing some energy to heat. Okay? Are any of these zeros? Now, kinetic energy is a half mv squared. What I'm really saying is there ever a time when our speed is 0? Which one? I'll give you a hint. It's either initial or final. Which one? Okay, so we can cross this out. Are any of the potential energies 0? Which one? Yep. So I end up with this. mgh initial equals a half mv final squared plus. Now I'm going to think about heat a little bit differently. Draw a little arrow pointing to the heat there. Heat is really the work done by friction. It's the work done by friction. Friction is what times what? Sorry, work is what times what? Wrong thing. Work is what times what? Okay, it's force times distance. Did they give me a friction force? Yeah. Now the force and the distance had to be in the same direction. Which distance in my DOLP is in the same direction as friction? The 3 or the 30? Yeah, the 30, because friction acts along the surface. So I'm going to argue that this is really going to be the force of friction times 30, and that's what I'm going to put down here. I'm going to put friction times 30. There's my heat. What are we really saying? We're saying, here's how much energy we started with. Most of it went into speeding up, but some got bled away into heat. And this is a much more realistic scenario than some of the ones we were doing yesterday. What are we? Oh, by the way, do the m's cancel here? No, they do not. Okay. I'm trying to get the V by itself. This is about where my liking of rewriting equations meets its limit. I could probably get the V by itself, but it's going to be kind of yucky. I'm actually first going to do some number crunching. I am going to minus the 200 times 30 over, so I'm going to go like this. A half mv squared, final squared, that's going to be mgh initial minus 200 times 30. And I'm going to crunch the whole right side before I try and get the v by itself. So what was m? They didn't tell me. Oh, what did they tell me? They didn't tell me m. What did they tell me? Oh, so mg is 3,000. Height 3 minus 200 times 30. That's equal to a half mv final squared. Crunch the right-hand side. What do you get? Oh, I can do that in my head for Pete's sakes. It's 9,000 minus 6,000, isn't it?
Yeah.
So 3,000, yes? And I have a half mv final squared. Now I'll get the v by itself. How would I get the v by itself? Well, I don't like dividing by a half. What's a cleaner way to get rid of a 1/2? Yeah, okay, so I'm going to go like this. Times by 2, times by 2. And then divide by m, square root. Now, they didn't tell me m. What did they tell me? mg. How can I convert that 3,000 into a mass? And you know what? I'm going to do that all in one step, I think. So I'm going to go like this. V final is going to be 2 times 3,000, all divided by, what was the 3,000 divided by 9.8? Square root. Am I wrong? Now, how would I type that? Probably I would go 3,000 divided by 9.8. I would do the denominator first, store that on my calculator, and now I'll go 2 times 3,000, 3,000 divided by answer button, store that on my calculator, and square root answer button. Again, some of you with the fancy schmancy displays can do that a little cleaner than I can. Mr. Dewick, with those 3,000s, as a matter of fact, those 3,000s probably would end up canceling in that fraction if I mucked around with it, but I wasn't that concerned with taking shortcuts this time. And I get 4.43, double check me, but yeah. Put your pencils down, look up. Homework part 1. We're going to come back to example 10. I have a similar one in the next lesson, actually. So I already said you could try 1, 2, 3, and 4. Okay? You can now also try number 7. Hang on a second here.
Excuse the interruption.
We'll skip 8. Roller coaster. Oh, 9 is good. 10 is good. Now 10, we have a change in speed. It says write a work energy equation. So you'll go change in potential plus change in kinetic, although you could probably cross out change in potential, and that'll tell you how much energy was used. It'll be the same, the change in kinetic energy. Skip 11, 12 is good. Skip 13, 14 is good. I'll leave 15, even though it's a roller coaster. So, continuing on. More conservation of energy. G. Slingshots. Bow and arrow. Anything where you pull something to store energy in there. The slingshot is pulled with an average force of 70 newtons for a distance of 90 centimeters. How much potential energy is stored in the slingshot? Now, potential energy Energy is the ability to do work. So really what it's saying is how much work was done in pulling this back. Work is equal to what times what? So this potential energy is not mgh. Gravitational potential energy is mgh. We're not changing a height here at all. It's going to be force times distance. I like this question. I like this question. I like this question. How much force did we use to pull this slingshot back? 70 newtons. What distance? 0.9, because it's centimeters. 7 times 9 is 63. 70 times 0.9 is also 63, yeah? We have stored 63 joules of energy in this slingshot. And that's why I'm calling it potential energy. I'm not calling it potential energy because it's mgh. I'm calling it potential energy because it's stored. If there is a 35-gram mass, how fast will that mass leave the slingshot? Now this is a job for conservation of energy because it's saying how fast. Are any of these 0? Because when you let go of the slingshot, all of the energy is expended. It's transferred to the mass. Before you let go of the slingshot, it's at rest. Now again, let me emphasize, this potential energy right there is not mgh this time, because there isn't a change. We haven't raised the height of this object. We have stored energy though, so this time I had to figure it out by saying, well, energy is the ability to do work, and work is force times distance. In fact, what's going to go there is 63 is going to be equal to a half mv squared. V final. How would I get the V by itself? Times by 2, divide by M. I got to be a little bit careful. Is the mass 35? No, it's grams. Okay. So, V is going to be 2 times 63 divided by 35 grams is how many kilograms? I know 0.035. Kilos out of 1,000. So it's not 0.35. That would be 350 grams. It's 0.035. Oh, and then don't forget square root, because this is V squared. How good are my numbers? I was trying to make up reasonable numbers. Do we get a reasonable speed? That's a crazy speed, but if I square root it... Yeah, okay. 63 meters per second. I've seen slingshots, so I'm imagining going out on the football field and it going about 2/3 of the football field in a second. You can follow it with your eyes, but it's moving fast enough you would not want to get hit by it. Yeah, that seems like a ballpark. Am I right? Am I wrong? Oh, you know why? Because I have answer buttons still programmed in here. Hang on. 2 times 63 divided by 0.035. Let's try that again. Square root. 60 even? That's a fluke. Still, that seems ballpark figure about right to me. Doesn't seem way too high or way too small. Little technical comment about ramps. We said that work equals force times distance, but the force and the distance had to be in the same direction. So since normal force is always perpendicular to a ramp, normal force does no work. And so if the ramp is frictionless, that means the energy of the system is conserved, which is why we can use it to analyze roller coasters. Roller coasters, they grease them down enough that they're nearly frictionless. Same argument applies to a rope. Tension is always going to be, if you imagine swinging on a rope, don't write that down, tension would always be along the rope, which is always going to be at exactly 90 degrees to the arc that you're tracing out when you swing in the rope, which means ropes do no work when you're swinging on a rope swing, which means energy is conserved there too. And so we can do Tarzan. Tarzan weighs 82 kilograms and can run at 8 meters per second. So we're going to have Tarzan here, Dulp. He's running as fast as he can. Well, no, not as fast as he can. He's running at 8 meters per second. And he's going to grab a rope swing. So here's our rope swing. And he's going to swing up. How high will he go? What's this question asking me to find, Josh? Height, that's a hint, because height appears in our conservation of energy. But really, is there a change in height? Say yes. Is there a change in speed? Is there a yucky, curvy path? This is a job for conservation of energy. Oh, did they mention work? Say no. You really overcomplicate it. Did they mention work? So I'm not going to solve this using work. I'm going to solve this using conservation of energy. I'm going to go, okay, kinetic initial, potential initial, kinetic final, potential final. Josh, are any of these zeros? Let's look at the kinetics. Is there ever a time when this person is at rest? Huh? Josh, you want to rephrase your answer? Where? Right? Imagine a rope swing now. How fast are you going at the very top of your swing for a split second? So we can go. What about potential energy? Are any of those ever zero? Are we ever on the ground? Where? Initial or final? Now, you could argue, wait a minute, Mr. Dewick. That's the ground. Don't write that down. But remember when I showed you that skate park, that energy skate park sim last day, I said you can put the ground wherever you want. Let's put the ground actually right there. And so I agree with you, Josh, we'll do that. This potential energy is energy due to a change in height. This potential energy is going to be mgh. So we have this. A half m v initial squared equals mgh final. Ooh! What do you notice? Is there an m in everything on the left? Is there an m in everything on the right? So here's what this means. Not only if Tarzan runs at 8 meters per second, but if Tantor the elephant runs at 8 meters per second and the rope doesn't snap, Tantor will swing to exactly the same height as Tarzan. Okay. We're trying to get the h by itself. How? Okay, so it's going to look like this. The final height is going to be, so Josh, there's a vi squared, yes? And then, Tato, what did you say we're going to do with the g? And then look up, look up, look up. Instead of writing 1/2, I'll just put a 2 there, and I'm not going to bother writing the 1 in front of the vi squared. There is a 1 there. There's a 1/2 there, but that looks cleaner. Yes? Okay. What was vi? 8 squared divided by 2 times 9.8, which is what? This will be the height. I can almost do this in my head. It's going to be 32 divided. It's going to be right around 3.3, 3.4? 3.26, 3.3. I got the 2 sig figs. 8 squared divided by bracket 2 times 9.8. 3.3, 3.26. 2.27, isn't it? Yeah, 3.27, I think. If I'm going to go to 3 sig figs. And that's meters. Slap shots are great examples of energy transformations. I wrote here video slap shots in slow motion. Do I have time to show it? Let me just check for a second. Slap shots are great examples. I'll try and find another time to show it. Roller coasters are also great examples. If the roller coaster just barely makes it over the first hill at A, so let's assume right here that VI equals 0. Yeah, barely made it over. How fast is it going at B? You good, Zach? You calculating or phoning? Okay. Wasn't sure. Zach, is there a change in height? Is there a change in speed? Is there a yucky curvy path? There's definitely a job for conservation of energy. And also, Mr. Duke, when do I use work? When do I use conservation of energy? Josh, this goes back to the question I asked you earlier. The question hasn't said, how much work? Okay. How fast? So, KE initial plus PE initial equals KE final plus PE final. Zach, plus heat? Why? Hey, ignore friction. Okay. Are any of these 0? What? So we're going to end up with mgh initial equals a half m v final squared. I gave you the mass of the roller coaster in the question. Did I need to give you the mass of the roller coaster in the question? How would I get the v by itself? Yeah. Times by, again, Tato, you could divide by a half, but I just think that looks ugly. The 2 in front is much nicer than a 0.5 underneath. This would be the basic equation for any roller coaster. I'm sure if you design rides, this is one you would have at your fingertips. Okay. Or you would actually probably reverse engineer. You'd say, how fast do I want to be going at the bottom? That fast. How high do we have to build the roller coaster? You'd reverse engineer. You'd solve for h. Anyhow, 2 times 9.8 times 18 square root 18.8. B. Suppose we had an initial speed of 22 meters per second. Instead of just barely making it over the hill, maybe this was the second hill and we already had some good momentum. How fast would we be going at B? A little better, because 18.8 is a pretty weak roller coaster. This is a job for conservation of energy. I think, Zach, we can still use your same argument for PE final, but not for KE initial, because now we're going 22. A half m v initial squared plus m g h initial equals a half m v final squared. Zach, have you gone on a roller coaster before? Did you step on a scale before you went on the roller coaster? Did they weigh you? Do you know why? Now, even if there was friction, as long as I make friction really, really tiny, it's called greasing the roller coaster down, it's negligible. I'm trying to get the v final by itself. I'm going to pull out that trick of clearing fractions again. I'm going to go times by 2, times that one by 2 as well, even though there's no fraction, times by 2. And what that will also do then is it'll cancel the 2 and the 1/2. It'll cancel the 2 and the 1/2. In fact, what I really end up with is vi squared plus 2ad, but it's gh equals vf squared. We get that third equation on your formula sheet from Unit 1 way back when. Oh, and then Zach wants me to square root. So our final speed at the bottom is going to be 22 squared plus 2, 9.8, 18, square root of what? All that. 22 squared plus 2 times 9.8 times 18. Oh, that's better. Little. 28.9 meters per second. Times by 3.6. Yeah, okay, you're doing 100 kilometers per hour. That's a pretty good coaster. That's a better coaster. But that earlier one, 18.8 times 3.6, that's doing city street speed. Meh. I mean, it might be thrilling, but I'm old school. Turn the page. Suppose the roller coaster in part B is only traveling at 25 meters per second at the bottom instead of 28.9 meters per second at the bottom. How much energy was lost to heat? This time we're going to include heat. Same approach though, Zach. It's going to be kinetic initial plus potential initial equals kinetic final plus potential final. But this time I'll add heat. I think we can still safely say that final potential is 0. We're still ending up on the ground. Nothing else cancels. Let's get the heat by itself. What will I do with that KE final? Minus it. I'm going to say that again for a reason. What do I do with that KE final? I like this question, I like this question, I like this question, but I don't know why, for some reason, when I give this question, kids divide by KE final. I've lost track of how many times I see them tell me, oh, it's KE initial plus PE initial over KE final. No, no. So don't do that. So if I hear you correctly, you're telling me the heat is going to be calculated by going the initial kinetic, the initial potential, minus the final kinetic, whatever's missing went into heat. It's going to be a half mv initial squared plus mg h initial minus a half mv final squared. Do the m's cancel this time? Well, isn't there an m in everything? Not in heat. So I did have to give you the mass. Okay. So heat, I'll do that in red because it's heat. It's going to be 0.5. What was the mass? 200, 250? What did I say it was? 255? And the initial, was it 22 at the top? Plus 255, 9.8, 18, minus 0.5, 255, 25 squared. I mean, this is a bit of typing, but it's actually a pretty easy calculation. What do you get? Probably going to get an answer in the thousands or tens of thousands, I suspect, but maybe not. And on this one too. Dope. Give me 1 second here. Continue 9.8 times 18. Take away 0.5. Come on. Take away 0.5 times 255 times 25 squared. I'm not confident that I typed it. Is it 27,000? Yeah. Holy smokes. Okay. 27,000 joules of heat. What else can we do? So roller coasters, by the way, to try and analyze this with a vector approach, but with a scalar approach, all it cares about, where'd you start, where'd you stop? We don't care about whatever the roller coaster did in between. Were there loops? Who cares? Did it go below the ground and then come back up? Who cares? Because whatever energy you gained, you lost coming back up anyway. So who cares? I like example 4. I like example 4. Example 4 is a nice question. A 75 kilogram cart and rider start from rest. That's probably important. On a 20-meter high ramp at the bottom, the car is traveling 15 meters per second. How much energy is lost to heat? Alec, is the same question I think we just did. It's going to be a job for conservation of energy. G. We're going to start up by going potential initial and kinetic initial equals kinetic final, potential final, and heat. How did I know to use conservation of energy? Because while the question asked how much energy was lost to heat. It's not talking about work. While are any of these zeros? Yep. Oh, this isn't too bad. So I think I'm going to get this. The heat is going to be potential initial minus kinetic final. Is that right, when I minus it over? Okay, plug and chug. Heat is going to be mgh initial minus a half mv final squared. Does the m cancel here? Not when there's heat. So it's going to be 75 times 9.8 times 20 minus 0.5, 75, 15 squared. How much energy ended up as heat? You get 62.5? So I'll keep this on my calculator, but I'll go 6260 joules. What I really like about this question is part B. Chang, what does part B want me to find? Friction is what times what? Did they give me a mu? Oh. What did I find in part A, Chang? What did I find in part A, Chang? What did I find? What did I find? And another way to think about heat, I think that was in our last lesson, actually. I think we said heat was also the work done by friction. Another way to think about heat, it's the work that friction did. It's the energy you lost to friction. In other words, the work done by friction is heat. Now the heat was 62.5. Work is what times what? So what would the work done by friction be? Force of? No, force of? You're way overcomplicating this. What would the work done by friction be? Force of friction times distance. So I'm going to argue that I can write this as that. How would I get the force of friction by itself, Chang? Which D? Look carefully at the question and ask, which D does the question give me that is in the same direction as friction? Yeah. So it's going to be divide by D. Friction is going to be 62.5. Now, if I really want it to be nasty, do we know friction now? Yeah? Now, once we type this in, do we now know friction? Now I could actually give you theta and ask you to calculate mu, because you would not get a normal force. It would be mg perpendicular. I could take that one step further. I don't think I would, but for what it's worth now, we're able to take some of our scalar data and go vector with it. You get 104.37, 104 newtons, because it's a force. Rube Goldberg machines are great examples of energy transformations. What's a Rube Goldberg machine? A Rube Goldberg machine is named after an artist named Rube Goldberg, who back in the 1930s and 40s and 50s was often an illustrator for, I think, New Yorker magazine, and he would design their back page where he would design an elaborate contraption to perform a simple task. So the task might be putting your toast into the toaster, but you would pull on a lever, which would cause a ball to roll down a ramp, which would bang into a bird cage, which would make the bird fly across the room and start pecking at some seeds, which would cause something else to fall. They were chain reaction machines, so we call these Rube Goldberg machines after the artist, and they're very popular to build, tricky to build, but you see a bunch of them on YouTube. Put your pencils down. Another great example of conservation of energy is a bouncing ball. So if I have a basketball, right now, what type of energy does this basketball have? Potential. And it turns into kinetic. Can you hear it? We're losing a little bit of energy on each bounce to sound and to heat, actually. In fact, you probably noticed when you bounce a cold basketball, what happens to it? It gets warmer, and the pressure, that's what you do in the morning when you pull the balls out of the car and they're all cold. Like when you go into a tournament or whatever, you're adding energy to the system. So here's my first question. Is it ever possible for a ball to bounce higher than when I let it go? If it bounced higher, what would that mean? That it had gained energy, and the energy ought to come from somewhere. So is it ever possible for a ball to bounce higher? So at the top of the bounce, let's answer these questions. Potential, MGH. What type of energy does the ball have when it hits the ground? No potential energy because it's on the ground. What's it all been turned into for a split second? Kinetic, that's when it's going its fastest. A ball loses height on each bounce. Does this violate the law of conservation of energy? No. Energy goes into heat and sound. Is it possible for a ball to bounce higher than it was originally dropped? You can cross out example 6 here. We did that already. We talked about how doubling the club head speed gives you 4 times more energy. Where doubling the mass only gives you twice as much energy. We talked about that during work. All right, a couple more toys. So, what's your homework? I gave you some last day as well, but you can certainly also then add to this from lesson 3, number 1. 2 is good. 3 is good. 4 is good. 5 is good. We'll skip 6. Skip 7. 8 is good. Skip 9. Skip 10. Skip 11. There is a 10. Yeah, there's 12 is good. Okay, what I really want to do is 14. There you go. I know I've thrown a lot at you. I apologize, but we need to practice this. I don't know. What? 14. I skipped 13, apparently. 12. 8. And then I think, what are there for 5?